So I want to prove one more uncertainty principle. See, the earlier uncertainty principle we talked about, that was about completely positive maps and why a joint measurement is not possible. That's number one. And if at all you have make any reasonable measurement, if you get reasonable information out of the measurement, that then the state will change. I mean, it will affect this. These two things we prove. Here we want to get a bound. If you have two random variables, x and y, self-adjoint, which are self-adjoint operators, then how much information? If you get more information of one thing, then you will not be able to get more information of another thing. So our setup, we know, I mean, our setup is we always, in quantum probability, we have a algebra and we have a state on that. Here we will work with, you can work with general Hilbert space, just self-adjoint operators, and you can have self-adjoint operators. Our Hilbert space is the quantum system, and you have a row on that. Row is a, for us, row is a, I mean, it's just row, and trace row equal to 1. Row is a state, it is just an operator like that. And X is a self-adjoint operator. Then we have, then, I mean, we assume, of course, you can, the same thing works for any H, infinite dimensional also. But if X is unbounded, if it is bounded, then the whole thing will work as it is. If it is unbounded, I mean, we will not be using anywhere finite dimensional, except we are working on finite dimensional setup, but we will not be using it here. But if it is unbounded, we can prove the same thing for unbounded also. Then you have to worry about domain where you take and all those things. There is something about domain you have to take care of. So that's all. Okay. So if we have any x which is self-adjoint, and suppose x is equal to summation lambda I pi, where this is a spectral decomposition. Okay. Of course, this is finite dimensional spectral decomposition. This is when it is finite dimensional. Then the probability of x equal to lambda I will be trace of rho pi. Okay. So this we know, and we can also talk about expectation of this. See, it is just x is self-adjoint operator. Once you have only one operator, then it is just a classical probability. X is just a random variable, mean it is just a probable. It is just a random variable on this. It takes the values lambda 1 up to lambda n. It takes, I mean, it takes the value. It is a random variable on the spectrum. With probability and probability of p equal to lambda I is this. This is so then you can calculate the expectation also. This is the expectation, usual probability expectation. So that is just going to be a trace of rho x. That's all. You just calculate, you will get that. Right? And similarly, variance is equal to expectation of x square minus expectation of, I mean, variance is usually, this is a formula, you know, in probability. Variance is this whole square, right? So, but that is equal to this. You can prove that simple algebra that this is equal. But in our case, when we state the theorem, which is called Heisenberg inequality or uncertainty principle, we will assume that the expectation of x is 0. So it is symmetric with, I mean, around 0. So this is the inequality theorem, Heisenberg inequality. The inequality says, say the case, so in physics, what we learned in, as a statement, what we learned in physics about uncertainty principle is you cannot measure both position and momentum. Position is a random variable, momentum is a random variable. You cannot measure both precisely. I mean, as precisely as you want. If you make the measurement of the position very precise, then the momentum you cannot have a precise measure. So the precision is given by variance. Okay? So it is just the statement about variance. So x, y, observable or random variable on H, okay, with and a rho is a state on that. If you fix a state, state on is a state. State on B of H means I would explain. So low is a state. Okay. Then such that, I mean, you have this E rho means expectation with respect to rho. E of x equal to 0 equal to E rho of y. Okay. Then this is just for simplicity. Otherwise, you can replace with, I mean, you can replace x with x minus ex, y minus ey, and work with that. You get the same thing. This is just for simplicity. It will not be very messy. Then variance of x times variance of y is greater than or equal to half 1 by 4 or half, I think half. I mean, half square will be outside, so 1 by 4 of trace of, this is what is called anti-commutator. Just write it, plus half of trace of xy square. Okay. And of course, these two are positive, so this is certainly greater than half of trace of y square. Where this is what is called anti-commutator, is xy plus yx. Okay. The xy and yx anti-commute, this is 0. Okay. This measures how much they anti-commute. But this is the commutator. Okay. If x and y commutes, then this is 0. This is the commutator. So if they don't commute, the commutator is not 0. And commutator is such that this is, I mean, it's a, sorry, there's I here. I here. Okay. And I mean, and this is a self-adjoint thing. Okay. And if it has a non-zero value, the trace will have a non-zero value. Suppose the trace has a non-zero value, then you have this square. Then the variance of x times variance of y is greater than or equal to that. That's a positive thing. So if one is very small, you want the measurement to be very precise, means this variance has to be very small. So if the variance of x is very small, this will be very high. So you cannot measure both of them together. That's what this says. So this gives a precise inequality. Okay. So we want to prove this. Variance of x, variance of y is greater than or equal to this. Once we prove this, of course, this follows. Okay. So proof. Of course, this inequality is basically follows from Cauchy-Schwarz inequality. In fact, that is the only inequality we have in Hilbert space. Okay? In every inequality, we prove it's a version of Cauchy-Schwarz inequality or some operator inequality. Okay? It's basically basic inequality is Cauchy-Schwarz. So well, it's a different version of Cauchy-Schwarz inequality. We have this. So let lambda. So lambda is a complex number. Okay? We take a complex number lambda, and lambda equal to r e power I theta. Okay. R is greater than 0, the polar decomposition. Then x plus lambda y star x plus. Actually, I mean, I'm not directly, I mean, it's actually Cauchy-Schwarz inequality, but I'm not using Cauchy-Schwarz inequality here. I'm using this operator. This implies trace of this is greater than 0. That's what I, okay. This is greater than or equal to 0. Okay. This implies trace of x plus lambda y star x plus lambda y is greater than or equal to 0. I mean, Cauchy-Schwarz inequality follows from the positivity of the inner product. So this is the positivity of the trace I'm using. I'm going to use. Trace of this is greater than or equal to 0. Then let's just compute this. This is just going to be x star x. I mean, trace, whole trace of this, x star x plus lambda is r e power I t minus I theta. I'm taking star e power I theta. Then yx, okay, plus xy r e power I theta for xy, okay, plus lambda r square, lambda bar lambda is r square, y star, y star, y star y is just x square. Okay. This is Hilbert joint. Is greater than this. Trace of this is greater than. Okay. So I can just write, I can write it there. R square trace of y square plus. So this is just, this is just the bar of star of this. So trace is bar star preserving. Trace preserves positivity, so it will preserve star. Okay. Trace is bar. So this is just, this will be just become, this is just the bar of, if you take the trace of this is bar of this trace. So it is just real part of that. Okay. So R is real, so you can take it out. So real part of e power minus I theta trace of yx. Okay. Okay. Right? That's what we get. So plus trace of y square. It's greater than equal to 0. Okay. Now this is a quadratic equation in R. Okay. It's a quadratic equation in R. And you know R is positive. R is greater than strict. The roots, it should have, these things are such that R is always greater than or equal to 0. It cannot be 0. So in a quadratic equation, something is strict. Quadratic, R is greater than 0. This quadratic equation, this value is greater than or equal to 0. Sorry. Whatever we have, this takes the value. This is a quadratic equation in R. I'm sorry, because it is a quadratic equation in R, which is positive, not strictly positive, greater than, which is non-negative. Okay, that is equivalent to saying the discriminant is non-positive. Okay, b square minus 4ac is non-positive. So 4ac is greater than b square. So here we have 2. This is 2 times the real part. So we have a 2 here. Okay. So b square minus 4ac is positive. Since we have a 2 here, so 4ac is greater than b square, greater than or equal to b square. So 4ac is this. So 4 will go cancel with the 2. So it is just trace of y square, trace of x square is greater than or equal to, it is just the b square of this. So which is just which is just the square of this e power real part of e power minus I theta trace of yx whole square. Correct? B, which is the b square. Okay. Now let's compute this real of e power. So which is just cos theta minus I sin theta. Okay. Okay. And then we have trace of yx. Trace of yx is, x and y are self-adjoint. Yx need not be self-adjoint. So we can write x and yx as real, self-adjoint part. There is a real part of any operator and the imaginary part of any operator. No? Which is, if you have a t operator t, then t plus t star by 2 is the real part. T minus t star by 2i is the imaginary part. So let me just write it. So that is the times. So that will be this xy plus yx by 2. This is the real part. Plus I times yx minus xy divided by 2i. Right? So this is the to get the real part, we have to multiply this. This is equal to cos theta times the whole square. The square is already, square. We have to get the square also. Cos theta into, that is just the anti-commutator, right? Y by 2, okay, plus I sin theta, I times I minus, which is 1. Okay, there is a 2, but there is a 2i, but this will become yx minus, that will become xy minus yx. So it is just I times sin theta into, there is a I here. I come, because this will, there is a trace of this. This will be, this, I will go inside. I times This is the common theta. Okay. I mean, it is yx minus xy. I have written xy minus yx. I've taken the minus, so there is I inside. This minus I into I will become 1. So here I have taken it this way, so I get a minus I here. There is okay. So this is what I get. Now I got the answer. No, I haven't got that. So we have got that trace of y square plus trace of, which is variance, which is which is just the variance, right? So variance of x square, variance of y square is greater than or equal to, we have the square of this, cos theta trace of xy by 2 plus sin theta trace of I by whole square. Okay. This is a skew Hermitian. Okay, that is why there is a I. I times this is self-adjoint. Okay, so these are all real numbers only. So, but you have a cos theta and sin theta. This is greater than this for all theta. Okay. For all theta in 0 to 2 pi or whatever. But you know this thing. I mean, if you have x cos theta plus y sin, this is just plus 2. I hope you have written JE and all. So this must be, you know, that this attains its maximum value. I mean, you can assume that you can, I mean, this has this x square plus y square will be the modulus of this, whatever. I mean, this will attain the maximum value, attains maximum when x and y are fixed at x by square root of x square plus y square, cos theta equal to this, sin theta equal to y by square root of x square plus y square. I will tell you orally the proof. You can just define x by this, call this as phi, cos phi, call this as sin phi. So then cos theta, sin theta, cos theta minus, it will be cos theta minus phi or something. And that will have the maximum value at 1 when theta equal to phi or something. You can work it out. Okay. So when theta, if you call this as phi, I mean cos phi or sin phi, whatever, then you will get an expression where theta minus phi will be, I mean, it will be easy as at 0, this cos theta, cos phi, sin phi, which is cos theta minus phi. So it will, the maximum value will be 0. So theta minus phi should be 0. So theta should be equal to phi. So this cos theta should be equal to the sin theta. So it will attain this maximum here. So now if you apply this, the maximum value of this, maximum value is x square plus y square. X square plus y square, I mean, what do we have to get? Yeah, we have to get the whole square. If you apply this, you get square root of x square plus y square down, and you will get, yeah, I will get, it will get x square plus y square, right? Maximum value of this is x square plus y square, where x square, x is this, y is this. That is what we want. Okay? That is precisely the statement. We wanted this square plus this square. So that is precisely what we have to. So we have got that. So it's proved. Okay? I don't have to write it, no? Yeah. Yeah, the maximum value of this is x square plus y square, and x is that, y is this. That's all.